Okay, Precalc AB students, Mr. Morris here. We're going to talk about right and left end behavior models. This example says, find the simple basic function as the right, and that is as x approaches infinity, and the left as x approaches negative infinity, end behavior model. So of course, we're talking about the right end of the graph as x approaches positive infinity, and the left as x approaches negative infinity. All right, so the way I look at this is which function controls, or which one has more power as you input larger and larger values. All right, so which one overpowers the other function? And so you might want to think of this when we're using positive infinity as y equals, whoa, does that every once in a while for some reason. So y equals, so think of this as y equals x squared plus 1 over e to the x instead of e to the negative x. All right, and so we'll bring the negative exponent down and make it a positive x. And so as x approaches infinity, let's look at 1 over e to the x first. When I plug in larger and larger values for x, e to the large number is a very large number. And 1 over a very large number basically becomes 0. And when I put infinity in for x squared, well, it gets larger and larger. So in this case, as a right end behavior model, it's just y equals x squared. X squared certainly overpowers 1 over e to the x when it comes to large positive values. All right, because you're going to take large numbers like say 1,000,000 and add it to basically 0. All right, let's see what's happening as we approach negative infinity. All right, as we approach negative infinity, I'm going to go back and look at this original form. All right, when I put negative large numbers in for x and I square them, they become very, very large. Now, when I put negative numbers in for x here, I get minus a minus, and that becomes a positive x. So now this is e to the x in the numerator, basically. All right, and so here's the question. Does an x squared outpower an e to the x, or does the e to the x outpower an x squared? Well, the answer to that is it's always the exponential. So now, notice in this case, though, it's still y equals e to the negative x as the left end behavior model, all right? And that's because when we plug in a negative times a negative becomes a positive. I know this is a little strange, all right? Let's do another one. All right, so here we have y equals x plus the natural log of the absolute value of x. And I don't know that we know the natural log of the absolute value of x, so let me do this. Let me lower this a little bit. And just below here, I'm going to graph only y equals the natural log of the absolute value of x. So let's start out first by graphing simply the natural log of x. So we should know this graph, and recently we talked about how important it is to know parent graphs. So we should know the natural log of x. When you substitute in 1, you get out 0. So the graph of the natural log of x will always go through 1, 0. So it looks something like this. So that's the graph of the natural log of x. Well, here we have the natural log of the absolute value of x. So what's going to happen here is we're still going to put in all the positive values that give us this graph to the right. But what happens when we start plugging in negative values? And of course, you can't plug 0 into a natural log, right? All right, natural log of 0 is not defined. All right, so let's just look at what happens when I plug in negative 1. When I plug in negative 1, the absolute value of negative 1 becomes positive 1. And so the natural log of 1 is 0. And I'm not really numbering these, I'm just talking about them, right? So this graph goes through negative 1, 0. Now, think about that. When I input a negative, it becomes its counterpart positive and should give me all these same y values then. So if I plug in 1.5 maybe here, I get this ordered pair right here, right? Or this dot. Well, if I plug in negative 1.5, it becomes 1.5 before I take the natural log, and so its output should still be the same as 1.5. And so this graph looks something like that. So really, it's just a reflection or a mirror image over the y-axis. All right, so now here's another one of these graphs that from now on, we will expect you to know the natural log of the absolute value of x, just like f of x equals the absolute value of x over x. So maybe start coming up with another long list of parent functions like we did earlier in the year. I think it was back in chapter 2, first semester. All right, so what's happening here is, and I'm going to use this graph to help us out, right? When I put large numbers, let's go our right end behavior model. And so as I put large numbers in for x, this goes to infinity, right? Y equals x, we know what that graph looks like. All right, when I put large values in to the natural log of the absolute value of x, see how this right here flattens out, all right, on this graph right here? And so large numbers added to these sort of small numbers are really just going to stay the large numbers. So this natural log of x graph will not really impact the x. So if I add 1 million to say, 1.5 or 10, it's not really going to change that value that much. And so in this case, as a right end behavior model, it's y equals x. And so the controlling function here of the two different functions is y equals x. All right, so what happens when I start plugging in negative values? Well, large negative values for y equals x become negative infinity. When I plug in large negative values into the natural log of x, it's on this side, but notice how these also flatten out. All right, now it doesn't become perfectly horizontal here, but it goes up very slowly and increases slowly. And so if I take negative infinity and I start adding some of these smaller numbers to it, it's not going to change it that much. And so again, in this case, because the natural log of x as x goes to either plus or minus infinity really flattens out, it doesn't change large numbers very much. And so in this case, the left end behavior model is the same as the right. Now that can happen. All right, so let's kind of backtrack a little bit here. The difference between finding these end behavior models and what we have done recently with rational equations, or which is really a good use of end behavior models, especially when we talk about the power in the top being larger than the power in the bottom, or the power in the bottom being larger than the top, or equal powers. These are not rational functions. What really is happening here is you have two separate functions. So in number one, you have back to this one, you have an x squared and an e to the negative x. In number two, you have an x and a natural log of x. So you have two different functions. And in these cases, you really have to analyze what's happening separately as you go to negative infinity and positive infinity carefully. That's why in number one, there are two different end behavior models, one to the right and one to the left. Number two, they're the same. All right. Okay. So I know that's a little tricky. Again, I just look at which function overpowers the other function as you put in larger and larger numbers, either positive or negative infinity. All right, so this is really kind of a review problem, but it relates back to just finding horizontal asymptotes and behaviors and then limits as we approach infinity. All right, so it says answer the following concerning f of x equals negative 4x cubed plus x squared minus 2x minus 1. Well, this is a polynomial, which is not a constant, right? And so it does not have a horizontal asymptote. So this question is fairly easy, although it can be tricky sometimes. It's none. All right, and we should know what the graph of this looks like. I'm going to talk a little bit more about that in a second. And well, let me step back a second. We don't know exactly what a negative 4x cubed plus x squared minus 2x minus 1 is, but we know what an x cubed or a negative x cubed looks like. And so when it comes to end behavior, all right, the end behavior, all we're really interested in is what is happening as you approach positive or negative infinity. And so the end behavior model on this is y equals, and that reminds me of something. I'm going to backtrack here again. But whenever you're writing, we talked about notation is very important in class. whenever you're writing a function, make sure you have y equals with it. Same thing on both of these. All right, so notice how I have y equals, all right? And then so down here, when you write the end behavior model, it's still a function. I just wrote y equals. I suppose I could write f of x equals here if I wanted to. All right, but y equals here is fine. All right, so because we're not really saying these are the same functions, definitely not. So this end behavior model is going to be just this lead term, negative 4x cubed. Whoa, pretty bad cube there, pretty bad. But we can always fix that. Okay, so now you could always think of this as this function over 1. And when we found end behavior models before, all we did is took the lead terms, divide them out, and simplify them. So this would be negative 4x cubed over 1. All right, so now how does that help us with C and D? I want to find the limit of f of x, our original function, not the y. I want to find the limit of f of x as x approaches negative infinity for C and as x approaches positive infinity for part D. Well, it would definitely help to know what this graph looks like, but I don't need to know the graph of the original function. This is where the end behavior model becomes so important. All right, so the end behavior model, all I have to do for end behavior, or as C and D are asking, as x approaches negative or positive infinity, is sketch a graph of the end behavior model. So this graph does something like this. Now, that's just the graph of y equals negative 4x cubed. Yeah, certainly the graph of negative 4x cubed plus x squared minus 2x minus 1 in the middle, right, in here may have some mins and maxes and some turning points. But since we're looking out at negative and positive infinity, we can use the model just to worry about what's happening as we put in large numbers for x, or large positive or negative numbers, meaning this will control the entire function as opposed to these smaller powered monomials that are part of the polynomial. All right, which is really kind of what's going on up here as far as what's controlling what. In this case, you have one function that are very similar monomials, and so the one with the highest power is the controlling function. All right, and so as the limit of f of x as x approaches negative infinity, so on my graph here, as we go to negative infinity, my graph goes to positive infinity, and so this is positive infinity. As x goes to positive infinity for part D, my graph goes to negative infinity. So this is negative infinity. All right, and so when you're looking at end behavior models, really there's only 4 ways this can go. If you have a negative in front, this cubic goes like this. So if this is an odd power, like a third, a fifth, a seventh, this would graph pretty much the same way on the ends. If this was positive 4x cubed, the graph would go like that, right? In the other direction. If the cubed was a even power, right? Then the end behavior are going to have values that go either both to positive infinity or negative infinity. So they will act just like a squared, even though it could be a fourth or a sixth power. So if it was like 4x squared, the end behavior model would go like that, right? And if it was negative 4x squared, it would go like that. And so there are only 4 different ways that end behavior models of polynomials can end up going. All right, that concludes the lesson for today. Have a great day.